using efficiency in very different contexts. So I think step one is just what do you mean by efficiency?
Okay, so in this case, by efficiency, I would mean the total amount of gas you have that's turned into stars. So not the local efficiency of the gas, but given it's like m star over m equal within the halo.
So I get my chance again. So I had a question about how you define burstiness. Burstiness is a timescale argument. And suppose you form stars on an orbital timescale with some efficiency, then in a very compact galaxy which has a small effective radius and also large rotational velocity, the orbital timescale is very, very short. So a star formation rate that appears bursty could still last 10 orbital timescales, and therefore is not at all bursty. It's just simply because the clock runs so fast that it appears bursty. So, so I'm not 100% sure that there's any burstiness. Just simply everything happens much, much faster because these are compact galaxies, and so the clock runs much faster. But nothing kind of special compared to the Milky Way, which has a long orbital timescale. So if you wait another 10 orbital timescales in the Milky Way, it takes 10 to 9 years, and these galaxies takes 10 to 7, 10 to 8 years. So I don't see it's extreme or anything different in physics compared to the Milky Way.
Well, so I think what people tend to be referring to, especially if you look at the simulations at high redshift, the star formation rates are fluctuating by orders of magnitude on short timescales. And so whether or not that's due to different physics or just different gas conditions at high redshifts, I think is a fair debate to have. But I think where this comes from is the fact that most of the early models, especially the semi-analytic models, were assuming these sort of smooth star formation histories where you assume sort of a smooth relation between MUV and star formation rate, when in reality, if you start allowing there to be some scatter between the sort of canonical gas accretion rate into star formation rate into MUV, that's sort of what we're trying to achieve here, is the fluctuations, particularly in MUV, where you get a sort of Eddington bias that can explain these high redshift galaxies. So we can, and bursty is sort of a buzzword, it can mean whatever you want it to mean, but I think the scatter in the MUV, I think, is much more concrete. Pablo?
So you haven't asked yet, but my first guess would be that the third is the main explanation because of several observables or several maybe prejudiced thoughts. Galaxies have to be younger. You are talking about very young universe, so maybe there were a few stars at the beginning, but they don't add too much mass, so any new star is going to shine like much more than the rest. So that should increase the mass to light radius, and we shouldn't use the regular recipes that we use for mass to light radius. Second, don't we believe that top 3 stars exist? That means that the IMF should be very different at the beginning, maybe very in a very short time scale, but it should be very different. And if we believe that top 3 stars are incredibly massive, several hundred solar masses or 1,000, then, well, the mass to light ratio is completely different. So I think the third for me, is the most plausible explanation rather than star formation efficiency. So a different mode of star formation at the very beginning of galaxy formation.
So I'll push back on that just a little bit, because I think you're totally fair to start playing with the mass to light ratio, and making galaxies younger, I think, is a very obvious thing to do, and that's naturally predicted by simulations, right? This is not something that just the observers would have problems with. You would get that for free from a numerical simulation. If you want to play the population 3 game, I think this is not the right way to go. And the reason I think that is because there hasn't been a single spectra that's been observed right now that looks anything like a population 3 galaxy. At least from predictions, there's been no 100 angstrom equivalent widths of helium-2. We also have no idea what the IMF is. I mean, you can look in the literature, and there's huge debates on what this is, with some people saying it's very top-heavy, other people saying it looks a lot more like salpeter. I think the best constraints we have on that are from the local universe, where we find no metal-free stars in the stellar halo, and that puts a lower limit on around roughly 0.7 solar masses. So yes, in that sense, it is a little bit more top-heavy, but in terms of what it's doing at the high mass end, we have no idea. Also, these population 3 stars, if they were massive, they explode very fast. And so the amount of metals you get quickly enriches you to population 2 mode. So a single 1,000 solar mass population 3 star doesn't have the UV magnitude that's detectable by James Webb at these redshifts. So I think it's a hard argument to make that these are population 3 stars.
And maybe another way to think about this is to essentially say, ask, is it something that can be explained with our common kind of baryonic physics model? Of course, you know, the densities are higher, so the star formation efficiency may change, et cetera, et cetera. Or is it something that needs additional physics, like a change in the IMF, early dark energy, et cetera, right? So my gut feeling is that we can probably explain it with, you know, common baryonic physics. The simulations struggle with reaching dynamic range, with reaching the high numerical resolutions in these more massive and brighter objects. So I don't know whether the results are converged. In the semi-analytic models, the challenge I see is that, you know, there are lots of free parameters, and you can probably kind of tune them to get what you want. So they have the challenge with the model degeneracy. So I'm not sure it's going to be easy to figure this out, but so my gut feeling is we may not need to go to exotic physics here.
Can I maybe argue a little bit against this?
Okay, of course.
So I think, as Rachel has explained quite nicely, up to 10 up to redshift 10 and 12, things sort of still work. But then if you go to 17, all hell breaks loose. And I think I just don't buy this argument of the increased density. If you go from redshift 0 to redshift 10, the density increases by a factor of 1,000. If you go from redshift 10 to 20, it increases by another factor of 10. So there must be something happening there, what we are not catching. And if we're just trying to keep this under the rug, we might be really missing something interesting. And I think this is at the heart why the hydro simulations struggle so much, because there isn't actually so much different at redshift 20 and 10 in the hydro simulations. There is no phase transition that really makes everything different. And it's much easier to do this in the semi-analytic models. You can sort of do something crazy and do a switch. But even there, Rachel found that if you change it and get it at high redshift, at redshift 10 and 5, it doesn't work anymore. So I think there's still something odd, and maybe you can sort of say that the time scales are obviously different. So once you hit sort of 100 mega years, if something is really different that's related to this, or with the metallicity that you really say that something happens between redshift 10 and 20. But I think the mean density of the universe, I would say, we will not be able to solve this problem.
I think Joel had
Since people have raised the question of POP3, I just wanted to ask if there are some POP3 experts who could clarify a few things. So 20 years ago, people were starting to do simulations of massive star formation, and certainly by 15 years ago, they were not finding... So the old argument for massive POP3 was Jeans mass, that you can't cool efficiently with just plain hydrogen. Even hydrogen deuterium doesn't help you very much. And as a result, you can't cool down to a very low temperature, and therefore you have to have a high gravitational force, massive galaxy, massive star rather, to counteract the pressure that survives because you can't cool enough. And so the typical mass you get is around 100 or a few hundred solar masses. That was the original argument. Then people started to do simulations, and they found that it gets more complicated for two reasons at least. One, there's angular momentum, and you end up typically in the local universe, massive stars almost always form in binaries or triples, hardly ever singles, and more so if you try to make massive things. And so that sort of counteracts the Jane's mass argument. And then moreover, you have to take into account what actually happens, sort of Eddington point. Once the thing starts to turn on and emit radiation, that can prevent further accretion. So that's sort of the end of the discussion as far as I remember it. Can somebody enlighten us as to what happens after that? What's the best guess as to what the masses of these top 3 stars actually are? That was question number 1. My question number 2 is, in the literature, people talk about peculiar metallicity patterns. For example, extra abundance of nitrogen as an indication that the metals may have been formed not in ordinary pop 2 or pop 1 stars, but pop 3 stars. What's the best wisdom on that, and what's the observational situation? This is a discussion session, so I thought, people aren't going for those questions, so I'll ask you a couple other questions. So are there any pop 3 experts in the audience?
I can comment quickly, Joel. So in terms of the IMF, there's like a geographical divide. So yeah, there's no consensus on this. So like if you look at really nice simulations by Shingo Hirano, like the Japanese collaboration, they can still get stars up to 1,000 solar masses, going down to 40 solar masses and below. Well, so that's the thing. The problem is that yes, the angular momentum fragments the gas, and so every simulation now sees this, but a lot of times those clumps then end up merging again, and so if you sort of push Western into Germany and then maybe even all the way to Texas, once you start getting into like the Arepo simulations from like the 2011s, I'm thinking of like Thomas Greif, Athena Stacy. Yeah, so those they can get stars down to 1 solar mass or even subsolar masses I was looking at. I think part of the big problem though is none of these simulations can actually bring you from primordial gas cloud into an actual star. They have to sort of simulate the protostellar accretion phase in 2 dimensions, and then it's super sensitive to what you assume for like the outflows, which nobody understands, the radiation from the star, which nobody understands, and sort of that's why the population 3 well, it's like the easiest problem in astrophysics. We know every single ingredient of population 3 star formation, and yet we still haven't solved it. So, I'll let a comment over there.
So, Joel, if you don't mind me reaching back to my days as a graduate student in Santa Cruz, which is ancient history. The thing I remember Stan Woosley talking about was that when you try to make a population 3 star, all you can do is initially run the CNO cycle, and that's not enough. And so you cook a little carbon with a triple alpha that you otherwise would never ever see. And so there you can build up, some of, and the CNO all goes to nitrogen, so you can build it up to a point where you're able to run some anemic CNO cycle and the equilibrium that way. But that's a very specific set of things that happen in population 3. And my question, knowing nothing more about it, is those who are doing nucleosynthesis, if they have really high fidelity understanding of exactly how you burn hydrogen with a massive, which is what you need to do this, population 3 star, because this is a very exotic outcome, but one that's expected. I think if you start with no metals at all, it will cook some nitrogen itself.
So that's actually how I define a population 3 star. So you can never rule out a minimum amount of metallicity from any spectrum, right? But if you can get it to the limit where you can't trigger the CNO cycle sort of naturally, which I think is like 10 to the minus 7 solar in terms of carbon abundance, that would be my robust definition for a population 3 star. Yeah, so it'll eventually do it, but it doesn't do it right at the start, right? It's got to build it up slowly, and then once it does it, it can trigger it on the
I'd just like to follow up on the point in pop 3 stars and the mass function. I still say there's broad qualitative agreement, if not quantitative agreement. I think across a large range of groups, there is clear signs that you form more massive stars. So the IMF is certainly more top-heavy than the present-day IMF. I think that is clear. I think it's just the question of how much more. And the question of low-mass stars, I think more and more groups are finding stars lower than 1 solar mass, especially if you add all the necessary ingredients. That's magnetic fields, the angular momentum in the disks, and you resolve the system as much as you can. But that is the key problem. Going back to Harley's point, even though the problem is very simple, it's the simplest physics problem that we have. It's also, compared to present-day star formation, it's also a lot more nonlinear, especially in the dense gas, because in present-day star formation, once you're in dense gas, you have the thermodynamics is almost purely set by dust, whereas in primordial gas, it's set by the interstellar chemistry, the hydrogen primordial chemistry, and you have things like HD cooling, which acts in very dense gas. So you got to couple all of this in together, and also eventually the feedback once the stars have formed. So in spite of it being a simple problem, I think it's still a relatively difficult problem in my opinion.
Any appetite to move to black holes? Always, yeah. So I can maybe start off with saying where I see a problem. I think JWST seems now to see black holes everywhere, and I would call that sort of supermassive seeds. So in the published models, people have sort of models where they have massive seeds, they have low mass seeds. What we are now seeing, allegedly observable, I would call supermassive seeds. I think if you would put this into your models, Rachel, you probably would get problems with a low redshift universe. You would have probably 2 massive black holes. So it would merge, it would mess up the low mass universe. Maybe not, maybe you should have a look. It's certainly not in any published models. And my naive intuition would be it might actually cause problems to put so massive black holes at this, so many of them so early, which would sort of, my favorite explanation is that many of these black hole masses are just not real. They're just wrong. Because people got carried away with interpreting a broad line as a mass of a black hole. They're not really measuring masses. They're inferring masses, and mostly they're just taking relation from spectra that look very different at low redshifts than they look at high redshifts. So that might just not work at all for most of the spectra.
So right now, this week in Ireland, there's a big conference on primordial black holes. And when you read AstroPH, every third paper is about primordial black holes. Yes, just primordial. And I actually should have been in Ireland. I never liked primordial black holes, but recently, I think this year, I wrote 2 papers about primordial black holes. And it's becoming interesting because there's now this string theory evidence that primordial black holes can't evaporate. So you have below a certain mass limit, you assume that the talking radiation erases them, but for whatever reason, I don't understand the details, the information can't get out quick enough. And so the evaporation is not happening. And then they can grow. And there is now a window of primordial black holes between asteroid masses going all the way to a tenth of a solar mass, which is interesting, where you can actually even explain dark matter. And I heard recently, actually from several sources, that gravitational wave detectors have found binary black holes with masses of a tenth of a solar mass. And there's no way you can generate a subsolar mass black hole by stars. So the only solution would be primordial. So maybe at some point we have to take it seriously.
Which gravitational wave detector could detect a 10th solar mass black hole?
course, is not high sigma yet. They don't publish. But when you talk to them, they say there's this evidence. Not only one, they have now several of these cases. So at some point, there might be something.
This is being recorded, so it's been first broken here.
I went to graduate school, and this is a totally unfair comment, but I went to graduate school in a department with a lot of string theorists. I'm not a string theorist. This is the first time that I ever heard the phrase string theory evidence. So I wanted to congratulate you for that.
I'm also sitting next to a theoretical physics department which is very critical of primordial black holes. And sort of, I got the feeling we have now too many black holes. When I was a grad student, it was a real problem to understand how you get the black holes in galaxies. And I felt the LIGO sources go a long way to solving this problem. So the LIGO sources had been much more massive black holes than anybody had expected. So when I was a grad student, it was believed that massive stars blow off the envelopes, so you wouldn't have any black holes that go above 30 solar masses. So now we have seen one that by merging of a binary has 150 solar masses. Sort of it's very easy to scale this up to 1,000 solar mass black holes in a star cluster. So the problem has become much easier. There isn't so much of a gap anymore from a 1,000 solar mass black hole to the 10 to the 5 solar mass black hole in the dwarf galaxy. So my preferred route is actually to do this in a dense star cluster and just scale up the LIGO sources, and then I don't need any additional ones. So it's interesting that JWST now sees black holes everywhere, but I don't think they're really needed to explain the black holes at low redshift, and I think if you put them in, you would probably find that you overdo it now. And I would certainly not open up the can of worms of primordial black holes just to explain the black holes in galaxies, even though they're very popular with many of my colleagues. But I think just for the sake of simplicity, I would say black holes are much less of a problem than they used to be 30 years ago. There's no reason to go overboard with too many channels.
So basically, yeah, if I wonder always why we have already a problem with cold dark matter. Now, if we add a warm dark matter component, what do we really learn from that? So, this makes everything even more complex if you have two types of dark matter, and then maybe have a dissipative component. And I don't really know. I agree with you. We should keep the parameter space as small as possible, but sometimes the universe is a little more nasty, and we need to take it into account, whether we like it or not. I mean,
warm dark matter initially was instead of cold dark matter. It was just not as cold as being completely cold. And there are models that produce cold and warm together quite naturally. At least there are particle physicists who push for this.
I think it's getting to be close to the time to stop. The banquet will be ready at 6 o'clock. It's nearly that. It's a short walk from here, and it's in the same building but on the ground floor instead of upstairs that it's been in previous years. So I can walk and people can follow, and also people who've been here before and know where the banquet is will also know where to go. So I think we should thank everybody from today, including, and let's head over to the hors d'oeuvres and then the banquet and the special program that has been organized by Rachel Somerville and friends.